let's take a look at some other numbers that people often like to throw around, or that numbers that are useful to know when we're coming up with policy on whatever the case may be. So we're going to turn our attention now to energy and see, and I'm going to put the caveat up front. Certainly I have my preferences for where we get our energy from, but I think we should get all the energy. Any energy that is available, we should get it, and we should use it and make people's lives better for it. So, and in particular, the energy that we get that has a smaller carbon footprint, the better. But overall, let's take a look at some of the energy choices that are put forward and see what the long-term consequences of these energy choices might be. So before we rush headlong into saying, oh yeah, that sounds like a great idea, we need to know if it's a good idea before we advocate for it, rather than just thinking it sounds like a good idea. All right, so let us take a moment and consider the following scenario. Let's go maps to Las Vegas, Nevada, because everybody likes to come to Las Vegas with the newly renamed International Airport, the Harry Reid International Airport, as opposed to the McCarran International Airport. So we have a new airport. It's has exactly the same shape as the last airport, but now it's new. All right, now right here, outside of Boulder City. So here is the road that takes you down to Phoenix, and then this road right here, this 95. That takes you down to Searchlight, which of course is the thriving metropolis where Harry Reid was born and raised, is Searchlight, Nevada, right here. So Searchlight, Nevada, the birth home of, or like at least where Harry Reid was raised, on your way to Laughlin, Nevada down here. But along this road, it's looks like a barren wasteland, but it is not a barren wasteland. It is teeming with solar panels. Okay, so if we zoom in at this dry lake right here, Boulder City dry lake bed, and surrounding this dry lake bed are a bunch of solar arrays. Okay, and there are a bunch of solar arrays on the north end of the city and on the south end of the city, so they're all over the place. So you can see these different things. They're roughly what? They're about a square kilometer, so this is about a square kilometer of solar paneling. So there's several square kilometers of solar paneling here, and then all this up here is also solar paneling for a bunch of different solar power generating companies. They're not all the same company, like Techren Solar, and then there's like I can't remember what all these different things are called, but they all have their own, Copper Mountain Solar, Nevada Solar One. So there's a piece of real estate that's been designated as eligible for like zoned so that people could put solar panels there, and so then they just farm it out, sell it off to different companies to put these things together. This looks like a parabolic dish kind of thing. That doesn't look like solar paneling. So this is a different kind of solar collector. You can see it's got parabolic dishes with some fluid running through the center, and so it gets hot and then sends it into some heat station, which is probably this one, some generating station. But these are solar panels. These ones are definitely solar panels. Let's see. So we start from something like this, and we see that it's about, here's a square kilometer. So there's, 10, maybe 15 square kilometers worth of stuff right here in this area. Now, this is changing constantly. There's always new stuff that's being built here, but at the time, this was rated, some number of months ago, this was rated at about 800 megawatts. 800 megawatts is a reasonable power generating station. So a typical generating station will be a gigawatt. So a large coal-fired power plant will be a gigawatt. A large nuclear plant, a single reactor nuclear plant will be about a gigawatt. So a gigawatt is kind of the unit that you use to measure electricity production. If you're less than a gigawatt, then you're not talking about providing electricity to a large metropolitan area. I think that Las Vegas takes something like 9 gigawatts. Peak capacity is somewhere around 9 gigawatts. I might be misremembering the number, but that's roughly what it is. So this solar stuff is 800 megawatts. Okay, now that's 800 megawatts on the sticker, but that's not necessarily the kind of mileage you get when you're driving. So the sticker on this is 800 megawatts, but that's full sun, everything shining on the solar panels all at once, and it stays there all the time. So, but you have cloud cover, you have the sun coming in at different angles through different times of the year, you have the sun setting at the end of the day, and so the actual electricity that's produced by this solar power plant is about 100 megawatts. So it's about almost 1/10 of the stated sticker power. So they'll say, it's 800 megawatts. That gives you enough energy to supply 800,000 homes. And the answer to that, and that's actually not true. It can supply roughly 1/10 of that because of intermittency and the solar angle and so forth. So that puts it 100 megawatts. If you look here at this right here, this is a power generating station that's a natural gas power plant. Just to give you by way of comparison, I think this is 3 gigawatts total on this one. This one we should probably look up. So I want the, what's it called? The something Edison, Edward Clark generating station. Edward Clark power generating station. Edward Clark generating station. The Hoover Dam is, I don't think is quite a gigawatt. We can take a look at that one as well. So this energy generating station is, okay, so it's one gigawatt. So all of these things combined together, they're natural gas plants. So these are probably all 150 megawatt, something like that, gas turbines. And they're different kinds of gas turbines. So, but altogether this is 1 gigawatt. So this is 10 times the amount of electricity produced here on that piece of real estate. And how big is this thing from one end to the other? So that's 100 meters. So this is about, so that's 100 meters. So there's 200, 300 by 300 meters, which is 1/9 of a square kilometer. Okay. So it's, you know, it would fit in here. That whole generating station would fit in here, and yet it produces 10 times as much electricity. So just by way of comparison, let's take a look real quick and see. Now, the Hoover Dam doesn't operate right now. The water's really low, so I don't even know if they're running electricity out of Hoover Dam. So Hoover Dam generating capacity. Whoops, Hoover Dam generating capacity. 2 gigawatts at the peak. So nameplate, so this is what you're looking for, nameplate capacity. Nameplate capacity is what they put on the sticker, but it's not necessarily what is delivered from one instant to the next. So 2 gigawatts is the nameplate capacity on that one. All right, so let's take a look and see if we converted, what kind of electricity, or like what would it look like in the distant future? And when I say distant future, I mean some number of years, a decade or so from now. What would it look like if we switched all of our electricity just to solar energy? So in order to do that, we need to find out how much energy the United States of America uses at any given time. So let us take a look at the Lawrence Livermore National Laboratory Energy Flowchart. And we're going to look at it from 2019, because that was the last year where things were normal. So in a couple years, we'll get back to normal again in terms of our energy use. But this is the United States 2019 energy flowchart. So where the energy is coming from and where it's going. I'm hiding part of this stuff right here. So let me adjust the size of this window so that I'm not hiding anything anymore. I want full disclosure here, because we want to make sure that the answers that we get are right. All right, so full disclosure is right here, energy services. So we get 32.7 quads is what we actually use. We lose about 2/3 of the energy to just heat that goes out into the environment because of inefficiencies. From what I know, the average US citizen uses way more energy than the average citizen in other first world countries. It depends on the first world country. So some countries, Canada uses more than the United States per person. But you know, every country, the United States definitely is among the top energy consumers. But Canada is worse, Norway is worse. It kind of depends on, you know, what's the local environment. Kuwait has a lot of energy consumption. All right, so what we were looking at, the goal was, what happens if we switch our electricity production over to 100% solar energy? Okay, so that would be, here's the energy that goes into electricity. These are the sources of energy that flow into electricity. And so we have 37 quads. Now, the total consumption in the United States in 2019 was 100.2 quads. So another reason to use the 2019 numbers is this is close enough to 100 that you can imagine these things as percentages, even though they're actually measured in some unit of energy. So a quad is 1 quadrillion British thermal units, because even though we kicked the British out 200 and something years ago, we kept their unit system. So 100 quadrillion BTUs is what the United States uses. Now there's a conversion between a quad and a joule, and that is the following conversion. And that is the 1 quad, excuse me, 1 quad. 1 1 quad is equal to 10 to the 18 joules. It's not exactly 10 to the 18. Well, why is it up there like that? 1 quad is 10 to the 18 joules. So it's 1.055 times 10 to the 18 joules. So it's 5% away. But this is a way that we can keep track of everything. So that is a quad. We have, let's say that we want to supply most of the energy needs for the United States of America through solar energy. And so if we come back to this energy flow chart, let's say that we need to get 10 quads because that's an easier number to work with. So this 13 quads is what we would need to deliver through electricity. But let's say that we're going to do 10 quads because there's some states that just are holdouts, like, and the rest of it's supplied by something else. All right, so we need to get 10 quads of energy. 10 quads. Now, the question is, how many joules of energy is this? We need to figure out what our power output is going to be. So 10 quads, and to convert this to joules is going to be 10 times 10 to the 18 joules. I want to keep this 10 out here because it's going to make the calculation a little bit easier in a moment. So 10 times 10 to the 18 joules. This is the amount of energy that we need to supply through electricity if we completely convert our electric grid from the mix that we currently have all over to solar energy. All right, now, the number of seconds in a year, because we need to figure out the power output. The number of seconds in a year is 3 times 10 to the 7 seconds. It's close to pi. It's 3.15 times 10 to the 7 seconds. All right, so if I divide this, I can get the amount of energy that we need. So 3 times 10 to the 7 seconds is 10 times 10 to the 18 joules divided by 3 times 10 to the 7 seconds gives us 3 times 10, like 10 divided by 3 is 3. And then this is 10 to the 18, and that's 10 to the 7, that's 10 to the 11 watts. 3 times 10 to the 11 watts is the amount of electricity that we need to provide on average over the course of a year. Now, this is going to be delivered by solar energy. The amount of energy we receive from the sun in direct sunlight. So let's pretend that we're working in direct sunlight. I'm going to round down a little bit because it makes the numbers easier to work with. The actual solar constant is 1,300 watts per square meter, but we're going to go with 1,000 watts per square meter because it's a little bit easier for me to work with. Okay, and this will make up the difference between, like, this 30% reduction here is going to be the equivalent of the 30% reduction from the energy flow chart. Going from 13 down to 10. All right, so, excuse me. All right, so 1,000 watts per square meter. So the question is, how many square meters of sunlight do we need shining on the Earth? So we're going to divide this by 1,000. Let's see. Yeah, so if I divide this by 1,000, I get square meters, right? Because I have watts here, I've got watts per square meter there. So when I divide the two, the watts are going to cancel. I'm going to get square meters at the top. So I divide those two, and I'm going to get 3 times 10 to the, that's 8. 3 times 10 to the 8 square meters of surface. So if we can capture all of the energy from the sun, we need 3 times 10 to the 8 square meters of solar energy to supply everything. So there we go. So this is important to remember. 3 times 10 to the 8 square meters. 3 times 10 to the 8 square meters. Doesn't sound so bad. We should be able to do that. Let me move this down one more time so that we can see all the numbers. All right, now the question is, what's going to happen long term? How do we get 3 times 10 to the 8 square meters of worth of solar energy? And what does that mean for the waste stream that's going to come down the road? So eventually these things are going to wear out. They're going to need to be replaced. And so what does that replacement schedule look like? So 3 times 10 to the 8 square meters. Now, this is if we could capture all the sunlight, but you can't capture all the sunlight. There are a couple efficiencies that you have to consider. One efficiency is how much sunlight do you actually get in a given day. So the amount of sunlight that you actually get in a given day is probably closer to 0.3. It's probably even less than this. It's probably more like 0.2. But let's pretend for the moment that we get 0.3 effective days worth of sunlight. So there's a 30% chance of, like, the fraction of sunlight. Okay, but then there's also an efficiency of converting the solar energy into electricity. What is the efficiency with which you can take solar energy and convert it into electrons that are moving through the wires? And the answer to that question right now is the typical efficiency that you're going to get over the course of the lifetime of a solar panel is probably close to about maybe 20% at the high end. So it's not going to be a very big number, but let's be generous. We're going to be generous in this because this is the future after all, and where we harvest unicorn poop and meet all of our needs through unicorns. And so let us give this a 0.3 efficiency, which is not what we get. But we're going to be generous here. So we're generous here on this one, and we're generous here on this one, that we're going to give solar energy kind of the benefit of the doubt on these things. All right, so let's take a look and see how many square meters do we actually need of solar panels in order to account for the fact that the sun, sets every day, and that there's this efficiency in converting the sunlight into other things. Well, that means that we need to divide this square meters by these numbers because we need more square meters. So if there's only a 30% efficiency, then we need 3 times the amount of stuff. All right, so I'm going to divide 3 times 10 to the 8 divided by, basically, this is going to be 0.3 times 0.3, right? I divide by both these efficiencies, like this. And 0.3 times 0.3 is going to be, what, 0.1? And so I need another factor of 10. I'm going to need 3 times 10 to the 9 square meters. 3 times 10 to the 9 square meters of solar paneling in order to supply this electricity. Now, we're not talking yet about, having energy storage on the grid in order to pass things around. This is just like the solar panels. Okay, 3 times 10 to the 9 square meters. Now, another question we could ask is, how long does a typical solar panel last? Does a solar panel last for 10 years? Does it last, on average, does it last for 10 years? Does it last for 100 years? The answer is closer to 10 than it is to 100, but let's be generous and let's say that they last for 30 years. So let's pretend that the solar panels are going to last for 30 years. So we're generous all along the way. For the most part, we've been pretty generous. So let's say 30 years is how long they last. So how many square meters of solar panels are going to be replaced, do we need to replace every year? So we're going to take the square meters, we're going to divide by the lifetime of those things, and we're going to get 3 times 10 to the 9, which is going to be 30 times 10 to the 8 square meters. And we're going to divide by 30 years, and that's going to tell us the number of square meters per year. This is 30 years. So those are going to cancel, and I get 10 to the 8 square meters per year. 10 to the 8 square meters per year. Now, how many does this mean per day? So we're going to take this 10 to the 3 times 10 to the, or the, I'm sorry, 10 to the 8, and we're going to divide by 365 days. Let's do 333 days. So we divide by 333 days because there are going to be holidays, right? So we don't want to necessarily do that. All right, so 10 to the 8 divided by 333, so that's going to be what? 1,000 divided by 333, and then it's going to be times 10 to the, that's 3, so this is 10 to the 5. 1,000 divided by 333 is 3 times 10 to the 5. 3 times 10 to the 5. 3 times 10 to the 5 meters squared per day. That is, it's almost 500,000 square meters of solar paneling every day that you need to replace. Now, if you get real efficiencies that are in there, you're going to have to increase this probably up close to about 1 million in order to accommodate for the downtime and like the realistic things that are in there, including losses within the electric grid, right? So there's already going to be a 10% increase in this because of losses in the grid. So, but anyways, we're more than 3 times 10 to the 5, or we're more than 10 to the 5, and we're probably around closer to 10 to the 6, which is 1 million. So anyways, 500,000 or 1/3 of a million square meters of solar paneling every day forever. Any day that you want electricity, this is what you'd have to replace. This is the waste stream. When people talk about different sources of energy and that the different waste streams from different sources of energy are going to be important, and a lot of times people focus on nuclear energy, which is fine because nuclear energy also has a waste stream, and we have to deal with what do you do with the nuclear waste when you're done with it. Same thing with coal. Coal produces a waste stream, and we have to deal with what is the stuff that comes out of a coal power plant, and how do we address the waste. The same thing with natural gas. The one advantage of natural gas is that, well, I mean, advantage in quotation marks about natural gas is that the waste stream of natural gas is a gas, and so we exhaust everything up into the air, and you can't see it very well. As opposed to coal, which produces a bunch of ash that then you put out in the parking lot or something like that, or nuclear, where you have the nuclear reactor core that's there. But all forms of energy are going to produce some amount of waste. And if we convert all of the electricity in the United States over to solar energy, then you're looking at something on the order of 1 million or 500,000 square meters of solar panels every day, forever. Any day you want electricity, you have to replace this many things. Now, we haven't yet run into this waste stream because all these solar power plants that are going up, they're being built right now. Okay, so the waste stream that we're going to get from solar energy, I'm not arguing against solar energy. I'm saying that what I'm arguing for is a realistic assessment of what it implies when we adopt a given policy. So if we were to switch completely over to solar energy right now, 20 years from now, this is what we're looking at, replacing this many square meters of solar paneling every day. So not a small amount. So something to consider is, given this aspect of the reality of the situation, does that change one's opinion about, is this what we really want to be doing when we produce electricity to supply society? Okay, now let's take a look at another example from this. So let us take a look at wind turbines. So I should point out that with solar energy, there are some things that you can recycle with solar energy, and there are some things that you can't recycle from solar energy. And even when you do recycle from solar energy, or like the solar panels, like certain aspects of it you can recycle, there's some energy associated with that recycling process. And so none of this is free. It's not like you just remove something and replace it, and there was no energy in the transaction of that replacement. So you either have to make new stuff or you have to recycle the old stuff. And the more you can recycle, the better, because then you're not piling up the waste. But not everything is going to be recyclable. And as time goes on, people can find other uses for things. But this is still the commitment that you're making, that one is making when you convert all the electricity to one form of energy. In this case, it was solar energy. Now, another thing I should point out is that is with the electricity production as it currently stands. Notice that of this electricity production as it currently stands, that only 0.03 quads, or 1/30th of 1% of the energy consumption in the United States goes into transportation right now. So if we want to electrify things and electrify all the cars, so we want to include the transportation sector here, then that's going to mean that we have to have an increase in the electricity production capacity. So let's pretend for the moment that we can supply all of the cars and that all the cars are 100% efficient. So if we can supply all the cars are 100% efficient, then this is the amount of energy that we need to supply onto the grid, which is 6 quads. Okay, that's basically an extra 50%. You take the electric grid that we currently have, and then you add another 50% to it in order to just supply the transportation sector. Now, there's going to be some energy losses here, so it's probably more like a doubling. So you have to roughly double the amount of electricity production that we have in the United States in order to supply the transportation sector with what it needs. So there's that. So that takes you from roughly 1 million square meters of solar paneling a day to 2 million square meters of solar panels per day if we want to electrify the transportation, which is fine. Maybe certainly electrifying transportation seems to be a worthwhile goal, but how you electrify it is the question that we're looking at today. So let's take a look at wind power. Okay, so what does a wind turbine look like? If you have a wind turbine, single wind turbine, so it's going to look something like this. Here is your thing, and then you've got these blades that are coming off. Here's this big spire that's like this, and you have these blades, and they're kind of long, especially because you get more energy if it has a larger surface area. The area that's swept out by the blades, the amount of energy you get goes as that surface area. It's basically the surface area times the wind speed tells you the power that you can get. And then there's some efficiency associated with that as well. So the typical thing is, like 5 megawatts is a large wind turbine, is something like 5 megawatts. Now this is a capacity, that's like their peak capacity, which is not, so then the question is, how often are they operating at peak capacity, or what fraction of peak capacity is the average operation for a wind turbine? So let's take a look and say, let's go with a 5 megawatt wind turbine and see what we come up with. These numbers I've already worked out So I pulled them off the internet so that we can look at them. All right, same deal. We still have 10 quads of electricity generation that we need to produce per year. We still have the 3 times 10 to the 7 seconds per year. So this is going to give us, again, it's going to be, 3 times 10, do we remember what this was? This is 10 to the 18, that's a 18, that's 3 times 10 to the 11. Watts? 3 times 10 to the 11 watts. Okay, and so how many wind turbines is that going to be? Well, if we have, let's say for the moment that we have 5 megawatt wind turbine, and do we want to, how are we going to make this easy for me so that I can figure this out? Because this is going to get into numbers that are harder to divide. Let's go with, let's say a 3 megawatt. We'll be generous somewhere else. We'll go with a 3 megawatt wind turbine, and we'll be generous in some of the other numbers. So this way I can work through it. So 3 megawatt wind turbine, and so that's 3 million. That's 3 times 10 to the 6 watts per turbine. Okay, so I divide these two things. The 3's cancel. I get here is going to be 10 to the 5 turbines. That's 10 to the 5 turbines if they are operating at their peak capacity. Now, typically, the effective fraction, and it depends on where you live. So, like some wind turbines are more effective, like more efficient than others. In other words, the wind is blowing more steadily in some parts of the country than in others. And the same thing's true around the world. So I had a number here of 0.3, so let's give it an effective, like how often it can do this, let's go with 0.5. And that will take care of this number right here. So let's say that it's 50% effective. Okay, so that means we need twice this many. We need 2 times 10 to the 5 turbines. Okay, that's 200,000 turbines in order to supply the electricity. And we're not dealing with intermittency. That's a separate issue, which also has its own waste stream. So if you're going to store things with batteries, then eventually those batteries are going to wear out. They have to be replaced. And that produces its own waste stream that's independent of the waste stream that we're talking about. So in this case, we need 10 to the 5 wind turbines in order to supply the energy demand that we have in the United States. And now the question is, what are you going to do with the wind turbine blades as they wear out? Because they do wear out and they have to be taken down and replaced. And the wind turbine blades, at least for the moment, are not recyclable. So they're big chunks of carbon fiber or something like that. And they basically get shipped up to the flyover country. They get shipped to Wyoming or South Dakota and then buried in landfills or just piled up in landfills in these states that don't have that many people that live in them. And so eventually, you know, it might be some consideration if Wyoming decides that it's no longer interested in storing the wind turbine blades from, you know, the Midwest. So something to consider is what these wind turbine blades. So let's take a look at what is the waste stream just of wind turbine blades alone. So we have 2 times 10 to the 5 turbines. Okay, so 2 times 10 to the 5 turbines. And what is, how many blades is this? So there's going to be 3 blades for every turbine. So we've got 6 times 10 to the 5 blades. Okay, 6 times 10 to the 5 blades. And how long do blades last? So blades last, what are we going to give them? Should we give them, if we give blades maybe 20 years? Is 20 years too long or too short? We can give them 30 years. So let's do 30-year lifetime, which seems long. I don't think that they can really last that long, but let's pretend for the moment that that works. So let us do 30 years. So if I go 6 times 10 to the, that's going to be 60 times 10 to the 4 blades, and I'm going to divide by 30 years, is going to give me, 2 times 10 to the 4 blades per year. Okay, 2 times 10 to the 4 blades per year. And then how many days are there in a year? Let's say that there's, I should have done 20 years. If I do 20 years, then this gives me 3 times 10 to the 4. 3 times 10 to the 4 blades per year. And then I'm going to divide by 300. Okay, and so this is 3 times 10 to the 4 is 300 times 10 to the 2. Right? There's 2 zeros and there's 2 more zeros. 300 times 10 to the 2 divided by 300 days. We're talking something on the order of 100 blades per day. Okay, so if we convert all of our electricity production over to wind power, then we're looking at something on the order of 100 blades per day that we need to to deal with, that we need to store. So, maybe it's a little bit less than this. It's probably more than this. It's probably more than this by about a factor of 2, but it's on the order of 100 blades per day. It's not going to be 10 blades per day. It's not going to be 1,000,000 blades per day. So we're talking about something on the order of 100 blades per day. Every day, this would need to be stored, or to somehow we need to deal with this waste stream. What do you do with 100 of these solar blades per day? Take a look at these wind turbine blades. So here's an article from Bloomberg that the wind turbine blades, they just pile up. So they chop them into pieces, and they store them in Wyoming. So Casper Regional Landfill in Wyoming. Of course, there's the Drum and Bugle Corps there, so that that's something. And there's opportunities for everyone in Qatar. So you can see them bulldozing over these wind turbine blades. So each one of these is probably, maybe a quarter of a blade or a fifth of a blade, something like that. So let's take a look at some other wind turbine blades so that we can get an idea. Wind turbine blades truck, and see how big these things are. So there's a wind turbine blade being pulled on a truck. So kind of a long truck. 100 of these per day. So you have 100 trucks with these blades every day. How long does it take to load one of these up and unload it and stuff like that? I mean, so we're talking not a trivial amount of waste that's going to come from these things. So it is true, you could make sailplanes out of this. You might be able to make houses and park benches and stuff like that out of them. But that's a lot of park benches that you have to make every day, forever. I think they're fiberglass, carbon fiber, some kind of, I look it up, but I don't recognize the name of the substance. So some kind of glass. Maybe they're made out of unicorn poop. So let's go what are wind turbine blades made of? And we'll do it over here. Epoxy, made with a fiberglass reinforced polyester or epoxy. So fiberglass reinforced polyester or carbon fiber or amarid Kevlar is also used as reinforcement. So you don't want them to be made out of metal, because you want something that's kind of flexible, so that they can withstand the constant flopping around in the wind. They do wear out a bit faster because one, they get coated in bugs, because bugs tend to fly at those heights, and so they get impaled upon these, or they don't become impaled, but they become spots on the surfaces of these blades. And also, if you have a lot of dust in the air, then the dust particles go by and the wind turbine blades hit them, and so they wear out faster than one might originally imagine. You might think, oh, these could last for decades, but if there's a lot of wind and there's a lot of dust in the wind, then it can wear the blades out pretty quickly. Is it toxic to bury them? Well, probably. The same as it would be toxic to bury other things. I mean, I don't think it's toxic the same way that, if we were to just dump nuclear waste on the ground, that would be more toxic. Or if we were to they're certainly less toxic than, say, coal ash tailings that you get from a coal-fired power plant. But a coal-fired power plant isn't producing the equivalent mass of these things. So I'm sure that they're not, really healthy for the plant life, but so they're probably on the lower end of the overall toxicity scale. Now look at this one. So wind turbine blades don't have to end up in landfills. So here's what this headline says. Wind turbine blades don't have to end up in landfills. And then it goes on to say 85% of turbine components can be recycled or reused. Okay, but that's the part that's recyclable and reusable. That's not saying the wind turbine blades. The blades are different because they're made of fiberglass to be lightweight and efficient. The mixed nature of the blade material makes separating the plastics from the glass fibers to recycle into a workable fiberglass material difficult. Where do use wind turbine blades end up? They end up basically in Wyoming. Let's see. Even though the waste stream represents only a tiny fraction of U.S. municipal solid waste, it's not an ideal situation. Only a tiny fraction now, when it doesn't contribute a lot to our energy production. But if we switch everything to that, then we're talking about more. Emerging innovations, there could be, I could imagine new technologies or new companies coming online to address this issue. Like what could we do with wind turbine blades when they're free? Maybe make roofing out of it or something like that. 14,000 wind turbine blades will be decommissioned over the next few years in Europe alone. In May 2020, the consortium produced Accelerating Wind Turbine Blades Circularity, comprehensive report which details design, research, and et cetera, and so forth. pyrolysis being developed, which are likely industrial with additional options for handling fiberglass blades when they reach the end of their use. This looks like a 2-blade wind turbine. Let's see. Anyways, I'm not convinced. Okay, this is going to make pellets can be transformed into a variety of products such as warehouse pellets, flooring material, parking bollards based on its demand forecast. Global Fiberglass Solutions anticipates being able to process 6,000 to 7,000 blades per year. Okay, so that would be kind of cool. Like, this is something, as these technologies are developed, as long as there's a market for people to consume them, then we don't have to do that. So, I support any thing that can use the waste in a useful way. But the point of the discussion here is that it's not free. Wind turbines are not without their own waste products. And so how do you deal with that stuff is an important consideration for before you go whole hog on like, this is what we're going to do and this is the future of our energy. Especially if you're selling it as something that has no waste or is producing no waste, because it only produces no waste until you actually have to tear everything down, and that is longer than the typical lifetime of a politician and their, or honestly, the lifetime of a CEO at the head of a company. They're not in the company for 20 years. A politician's not really in office for 20 years. Some are, but most of them aren't. And so what do they care about a waste stream 20 years? And 20 years from now, it's a different voter base. And so you can sell people on something else. So there we go. This is a couple calculations that are useful to go through. 100 blades per day, or a square kilometer, basically, of solar panels every day forever, for as long as you want electricity. That's what we're talking about. So these are some, I guess, interesting calculations that to consider when putting forward solutions for the challenges we face with energy. All right, let's see. Any questions? Let's see. It would also take more land than solar does, wouldn't it? The land footprint per blade is quite sizable from what I understand. So the land footprint per blade is pretty big. You have to spread them apart. And so a lot of times when they do like how much land is taken up by a given technology, with wind turbine blades or with wind turbines, the footprint of the turbine is really small, but there's a lot of unusable airspace around them, and they have to be fairly widely separated. So it depends on, do you do only the footprint of the base of the tower, or do you do the footprint of the base of the tower and the 360-degree swiveling of the blades to account for, how much land does it actually take to do these things? So it's kind of it's a messy business. And the question is, do you want to tell people something that is true but also misleading? I feel like eco-solutions should be done at the individual level. They can be decentralized. Yeah, I agree that my opinion is that renewable energy, that kind of thing, is a local solution or a part of a local solution. It's not something that works everywhere. The wind doesn't blow the same everywhere. And so where the wind blows, it makes more sense to put wind turbines, provided that it makes sense in the first place to make a wind turbine. The same thing is true with solar. Whenever you're using a diffuse energy source, it's too expensive to move that energy source from one place to another. So if you're using a diffuse energy source, which all renewables are basically diffuse energy sources, you can't deliver that energy source to a distant location unless it's through the grid, and the grid has its own losses. And so, and most people get power basically that's generated fairly close to where they live. If you have an energy source that is really spread out, you can't transport it from one place to another very easily. Where if you have something like, that's one of the reasons that people use fossil fuels a lot, is because fossil fuels are energy dense. And so if you do transport them from one place to another, it only represents the energy consumed in transporting them from one place to another is small compared to the energy that gets released by the substance once you actually use it. And with nuclear, you get that by a factor of 1,000,000, because nuclear energy has 1,000,000 times the energy. Nuclear fuels have 1,000,000 times the energy density of fossil fuels, and so it makes even more sense to transport nuclear from one place to another as needed, because the energy density of the nuclear fuel is so high. All right, let's see. Aluminum specific strength stiffness won't allow for them to be so large. Wind turbines are noisy. I've not lived underneath a wind turbine. I don't know that I would want to live underneath a wind turbine, but The place where I saw them the most was in Indiana when we were driving through Indiana, and they popped up all over the place. Would it make sense to continue a pie chart style of energy production and phase out the oil? So it depends on what you want to use the oil for. So in the United States of America, the oil is used primarily for transportation. There is some oil that's diverted to industrial applications. So this is probably like plastics manufacturing and stuff like that. I believe that the industrial application here also includes the oil refining process, because they typically burn some portion of the crude oil in order to supply the energy to distill the rest of the oil, like to refine the rest of the oil. And so I believe that some of this petroleum, it's something on the order of it's between 10 and 20%. So let's pretend that it's 10%, although it is slightly more than that. So 10% of the oil that goes in here, so that's going to be 2.5 quads. So there's 25 quads that goes into transportation. So 2.5 quads, which is about a third of the stuff that's coming up here into the industrial portion. So it's between a third and a half of the stuff going up to the industrial portion is going to be devoted to the refining process. I believe that that's how they account for this. The transportation is only the direct use of the material. And so what's really going on is that all the petroleum is going through the industry. Some of it gets burned off, and then it gets piped back out and run through the transportation sector is what's really happening. Let's see, carbon sequestration using used windmill blades to store CO2 under high pressure in the ocean. I don't know if it can actually hold it, but you're saying like make a cannelloni out of it, where you stuff the turbine blades with some kind of carbon material and then put it underground? Yeah, hey, maybe. How does the comparative space required for storing atomic waste? Atomic waste is tiny compared to all this stuff. I think all the nuclear waste in the United States right now would probably fit inside a dozen wind turbine blades, like the equivalent of a dozen wind turbine blades, maybe 100 wind turbine blades. So nuclear waste is small. One of the issues that is being addressed by another company, we've looked at it once before, which is called deep isolation. So deep isolation, this nuclear waste team of people looking at nuclear waste disposal solutions, their solution is the following. So using horizontal drilling techniques, which have been used a lot in the last, 15 to 20 years for oil extraction and for natural gas extraction. So you have the surface up here, and you have the water table. The water table is the main concern, in my opinion. There's certainly other concerns, but the water table is kind of the big one. So here's the water table, and you don't want to store. The challenge of storing nuclear waste above the water table is that it can leak down into the water table, and then it goes everywhere. And so Yucca Mountain is in kind of a dry area. You have a mountain, and then you can deposit something up here so that it's kind of isolated from the water table to a fair amount and is embedded in some kind of rock that's going to stay stationary. What deep isolation is doing is saying, okay, the water table, this is typically going to be something like 100 feet down, because you have to be able to drill a well to get down to the water table, so it can't be too deep. So 50 to 100 feet, maybe 20 feet in some cases. It's fairly close to the surface. What deep isolation is saying is, okay, we're going to drill down a tunnel way down here, way down here. You can't see where it's cutting off. Okay, so this, instead of being 100 feet, or let's say that this is 50 feet, because then I can do the math, this is going to be like 5,000 feet. So it's 100 times deeper. So to do this to scale, it would be, here's the surface of the Earth, here's the water table, like that, right underneath it, and this would be clear down here. Okay, so this is like, say, 50 feet, and this is at 5,000 feet, 100 times deeper. So you drill a hole down here, you drill a tunnel out to the side, because we have the techniques to do that, and then you just take these spent fuel canisters and then run them down, and you store them up like this. And so you have all the canisters piled up like this, and it's so far below the water table, because this isn't even really to scale. This is probably 20. So you probably have to increase the distance here by another factor of 5 or so to get it actually to scale. But this is so deep below the water table that there's no chance of this stuff, even if it broke open, the diffusion time to get this stuff up to the water table is like millions or billions of years. And the half-life of the material is going to be like 100,000 years. So at the worst case scenario is that the half-life is about 100,000 years. Most of the stuff, the half-life is more like decades. So depending on which part of the waste you're talking about, but like decades to maybe centuries, with a few elements that persist for a lot longer. And this is so far out of the way of everything, it's pretty deep down into the crust. And there's rocks that have been basically undisturbed for billions of years on the Earth. So some of the older rocks in Canada, northern Scandinavia, there's a lot of rocks that have been basically undisturbed almost since the Earth formed. All right, let's see. The energy graph in petajoules, how to convert it to pure joules. Petajoules is what, 10 to the 15? Petajoule, 10 to the 15 joules. That's how you do it. For my country, the graph is in petajoules. There's actually a low-level radioactive waste. Let's see. There's actually quite a bit of low-level radioactive waste. What is the WIP site started? That I don't know. Now, one of the things to consider also with some of these things is that there is often radioactive stuff that gets unearthed in the production process for almost anything, because uranium, thorium, these are elements that exist in the crust. And so whenever you mine anything, you're going to be exposing some of that stuff back to the surface of the Earth. It's already there to begin with, just below the surface of the Earth, so I don't think it's a huge deal. SMR is a mini nuclear reactor. Yeah, so small modular reactor is typically something like 100 megawatts instead of a gigawatt. So you would put 10 small modular reactors together to make a big conventional nuclear reactor. Unicorn poop is like the thing that makes everything work with no waste at all. So there's no downside, it's all upside. Let's see, always interested in researching methods in reducing half-life of byproducts rather than putting it in glass. So the only way really to reduce the half-life of byproducts would be to change the nuclear structure. So you would maybe bombard it with a beam of neutrons, which is kind of what happens in the reactor itself. So you could imagine if you have a reactor where the fuel is liquid, so this would be like in a thorium reactor. So the fuel is liquid where you can process it in real time, then you can extract. So there's certain isotopes that could be a bit of a challenge, but if you had the odd numbered isotopes, they tend to have shorter half-lives than the even numbered isotopes. But anyway, so you're processing it in real time, and you could extract the neptunium instead of the plutonium, and maybe neptunium has a shorter half-life, and so you just put the things with long half-life back into the reactor and let it react with the neutrons, and then you specifically extract the shorter-lived half-lives of the interleaving ones. So if you look at the periodic table, I don't know all the half-lives of these things, so I'm just kind of thinking off the top of my head here. But I think that neptunium has a shorter half-life than plutonium, and protactinium has a shorter half-life than thorium or uranium. So if you start with thorium, for example, you build up your uranium fuel, because you're using uranium-233 in a thorium reactor, and you can build up past plutonium and americium and curium and just extract those elements that have shorter half-lives than the other ones in real time, as opposed to with solid fuel where there's no way to process a solid fuel without kind of pulverizing it and doing a bunch of chemical extraction. If it's already molten, then you can do it in real time in the salt. So that might be a possibility. Let's take a look at the half-life. See one step further and see if this is a plausible scenario. Half-life of nuclear waste, and there's I think this one is going to have the graph. Let's see if it has the graph. Not see it. Here we go. This is the graph we're looking for. Okay, so neptunium, uranium. So we have americium here that is 4,000 years. So another thing to consider. So sometimes people will say some of this material is going to decay and it turns into something that lasts even longer. But if you have something, say you have americium-243 and it decays or something happens to it and it turns into americium, there's nothing in here. But it turns from americium-243 into some daughter particle like uranium-236, and they'll say, the half-life is now longer, but that means it's less radioactive. If you have something that has a longer half-life, then it's less radioactive. So it stays radioactive for longer, but it's less radioactive overall. And so you could take something, you could imagine taking something, well, these are kind of big, but suppose that you have protactinium or plutonium that you make, this plutonium, and you keep it in the neutron environment. You could go from plutonium-239 to, say, americium-243, and then that cuts you down by a factor of 4 in time. This is probably more dangerous than the plutonium is. But then if you keep going, you can go to berkelium-247, which cuts you down by another factor of 4. And then what else is available? So if you, or americium-243, if you could get it to californium-250, then you're talking about 10 years. So if you can get the stuff to turn into californium, then it only lasts for 10 years. And that you can put almost anywhere. I mean, you want to have it isolated and you want to have it shielded, but it's only got a 10-year lifetime, which is easily something that we can handle the storage of something for 10 years. It's these ones that are 10,000 years that are the problem. So that's one possibility, is to keep it in the neutron-rich environment until you get up to, what's this one? Curium? I don't know what CM is. CM. Curium. Yeah, curium. Or californium, or whatever this thing, actinium. Anyway, so something to think about. Berkelium, 141 years for berkelium. What does it say? So anyways, that's something to consider. Waste isolation pipeline underground storage facility in New Mexico, Salt Dome in New Mexico. I wouldn't wait for fusion. Fusion is probably 100 years away from now, in my humble opinion, because they haven't even turned it over yet to where you get more energy out than you put in. And one of the things that was pointed out, and this goes to science communication and the challenges that you face with science communication and the ability to tell people something that they want to hear and deceiving them about, like, you can tell someone something that's true and also deceive them at the same time. So when people are talking about nuclear fusion, and they're talking about like the energy balance and how much energy do you get out compared to how much you put in, it's right now the quantity that people are using for this is a ratio. Like, if you want to make fusion happen, there's some amount of energy that you have to put in, okay, like this. So say this is all the amount of energy that you have to put into the nuclear reactor, the fusion reactor, in order to get some amount of energy that comes back out. Okay, and so then the question is, when do these things balance? When do you get more energy out than you put in? Right now, as far as I understand, and there's a YouTube video about this from Sabine Hassenfelder, where she points out the fact that the ratio that they're actually using is not all the energy that actually goes into the plant. It's the energy that goes into some aspect of the interaction and not the energy that goes into making the whole plant work in the first place. And so it's saying, here's the energy that we get out, and we're only going to consider this much energy that we're putting in. So we're going to consider this much energy, and we're going to ignore this much energy here, which might be the stuff going into making the magnetic fields or something like that. It's just the interaction energy that goes in. And now they're saying, look, we broke even. And then people are going to say, yay, now we can do fusion energy right now. And it's like, they're not even because they're not considering the energy that goes into operating the plant itself. And so if that's true, and she says, she goes through the outline of like everything, which I'll pull it up so that we can see the video and people can look at it on their own. Sabine Hassenfelder, nuclear confusion, this one right here. So this video, she goes into like what they're actually using when they're claiming that they're making progress in terms of what does it mean to get positive energy back out. And it's not what we think it is, or it's not what people imagine in their heads when the number is communicated. And that's a problem. And I agree with her. If that's true, which she says that it is, and she explains like what it is going on, so I have no reason to disbelieve her. So if that's true, then that's terrible. Okay. Yeah. So that is, so be advised, there's no universal solutions. All things come with some kind of trade-off. And so we need to figure out like, what are the things that we're willing to do in order to have an energy rich future, where people don't starve to death when they're age 42. Like, one of the reasons that we need more energy today, and then one of the reasons that the population of the Earth has grown so much in the last half a century, is because there are more people eating more food. Like, people live longer. And so when the life expectancy goes from 60 to 80, then all of a sudden the population is going to go from 6 billion to 8 billion without changing anything. So at least for that period of time while people are still alive. So yes, I agree. It is a big step in proof of concept, but it's going to be sold as something that it's not. It's going to be sold as something that's not by either reporters who don't know any better or scientists who do know better and are still interested in.